P.2quared journal, entry 15, Helix, part 6. Today is October 31st, 2021. Time is 5:04 a.m. So in the last entry, I said that in this entry we were going to discuss weak force and radiance. And after thinking about how I have neglected to focus on how this hypothesis synthesizes with our observations that we have classified as weak force, I don't think it would be wise for me to discuss the application of this hypothesis to what we know about the weak force. I am not as informed of that area as I would like to be, so we're going to skip that. In fact, we might skip that for a while. That might not be discussed until I've actually had a chance to study physics properly. But what I can talk about with a lot of certainty at this point is radiance. So instead of discussing weak force, today we're just going to discuss radiance, meaning we're going to talk about photons and gravitons, and from the view of this hypothesis, where those particles come from. So when you have two particles that are sitting next to each other, doesn't matter what they are, they're going to have interactions between their constituents, and those constituents are going to become a tangled mess of another particle. When this happens, this right here is what creates particles. This is the birth of a particle, two constituents getting tangled together. So the characteristics of this new particle are dependent on the parent particles. So if a particle is spinning very quickly, the child particle will also spin quickly. The vector of a particle will also decide the vector of the child particle. Now, the only interesting part about this is, in order for this hypothesis to make any sense, a constituent has to travel much faster than a particle itself. We have clocked particles going at the speed of light, but what this hypothesis suggests is that in the interaction between particles is happening at faster than the speed of light. So, well, you have a particle here and a particle here, and these two particles are traveling at the speed of light. The interaction between the two is actually happening at a much faster pace. That's how you can have, for example, let's go like this, a wave, right? Because these two particles are interacting with each other. I expected that to do something that it didn't do. Sometimes the app works, sometimes it doesn't. And so when you look at a photon, for example, a photon would come from two negatively charged particles sending their constituents off in a way where they can get entangled with one another and then fly off. Now, this would happen in waves, and especially if you're in a high kinetic energy system, this would happen more often, because you would have the entirety of the electron shells coming together, getting in very close proximity to one another, and making a lot of constituent bonds as they are repelling each other, right? So let's clear real quick. You have an atom. It's very poor drawings. Electron shell. As these two guys move towards each other, the first thing that they're going to be be interacting with is each other's shells. So there would be a lot of constituents flying in all sorts of directions. Well, that's not true. Beginning to get entangled with one another, sending off photons from these interactions. Now, this is well known in physics. You have two electrons, you push them together, they fly apart, and a photon flies out. Where this hypothesis gets interesting is these guys also have nuclei that have positive particles in them. So we're going to look at the up and down quarks, right? So we're going to look at a proton. So we have up, up, down. So these two positive particles are also interacting with one another. And since they have a positive charge, what we could assume, just like when two electrons come together and a photon pops out, in this instance, because these two up quarks, positive particles, are sitting next to each other, that a particle would come out of their interactions as well. But these particles would not be negative, they would be positive, like their parent particles. Now, the interaction between a positive and a negative particle, an up quark and a down quark, would give you a neutral particle, so we could assume that that's where neutrinos come from. But gravitons would just be a photon with very low spin, giving it a positive charge. So considering that the universe is full of these positive particles just sitting next to one another, we can imagine that the entire universe, every atom in the universe, is just spewing out tons of positive small particles. We would have never seen them in any sort of interaction simply due to the fact that gravity is everywhere. We kind of take it for granted. The fact that one of these particles can pull this thing down is evidence enough. Even though I read something on a science Instagram page that I thought was very reputable. They were talking about the graviton, and they said we have no evidence of a graviton particle. And I thought that was very odd, since gravity seems to be everywhere. So I'm sure that there's a more technical reason that that post said that you don't see evidence of a graviton, but I kind of think that this is like a fish discovering water. It's very hard to discover the thing that's everywhere. But if the Helix hypothesis has any merit, gravitons are very simply positively charged radiant particles. And those positively charged radiant particles are what's pulling everything down. Now, the interesting part about this interaction specifically is that it is far less frequent than the interaction of, let's say, electrons, which is why you would see a far weaker gravitic force than when you compare it to like the electromagnetic force. Because in an atom, you have this tiny little positive group of particles in the middle, and then an entire cloud of negative particles, meaning that sheerly by the number of interactions, you're going to have far more negative particles in the system than you are positive particles, which means the chances of you interacting with a positive radiant is far smaller than you interacting with a negative radiant. That's radiance. That's what I wanted to talk about today. We'll work our way back around to weak force eventually. But I think that this kind of sets the stage enough for a movement into a discussion of macroscopic aspects of this hypothesis instead of just a microscopic aspect, instead of just the microscopic aspects of this hypothesis. I think I got through the whole podcast, or the whole entry, without saying theory once. Getting good at this. Anyway, we'll move into how this affects, for example, time dilation and all that, and what its implications have. There is one thing actually that I forgot to mention, and it's that in this hypothesis, it's very possible for the radiance to actually accelerate. What I mean by that is that you have these waves of particles traveling, and as this wave travels, they interact with each other. That is terrible. I'm a terrible drawer. But then, as they're interacting, they're making baby particles. And these baby particles would actually have to travel faster than their parent particles in order to conserve both the wavelength and the amount of energy that wavefront has. So that's kind of a big one. That's something that we haven't observed yet. But truthfully, when you look at what we're observing, when we are making observations about the speed of light, we're either, if this is the Earth, we're measuring at one constant gravity, right? Or we have nice little satellites up here, and then a satellite over here. And as far as I am aware, we don't ever have satellite-to-satellite communication. Instead, we always bounce it back through Earth and then bounce it up to another satellite if we want to communicate. So we haven't done too many experiments, as far as I'm aware, in low gravity to see if there is a difference in communication speed when you are in a medium that is not as gravitically dense. And I think it might take us getting into deep space, where we're not affected by the sun's gravity, where we'll start to see the infinite acceleration of light, as long as it's not hindered by anything. But we'll get into that more when we get into a discussion of time dilation and stuff like that. But that's something I didn't want to move on. We can't end this entry without stating that radiants accelerate infinitely, as long as they don't have a hindrance. So anyway, I hope this made sense. I hope my rambling made sense. And until the next one.